Thank you, Bambi, for the introduction. Solid propellants are used in propulsion systems in aerospace and defense applications. And the most popular solid propellants are the composite solid propellants. These materials are heterogeneous materials that are composed by ceramic oxidizing particles that supply large amounts of oxygen during the combustion process in the operation. Metallic particles to enhance the combustion process and to give shape and a structural entity to this energetic material. And elastomeric matrix is normally used. Of course, the mechanical response of these composite materials is very complex because of the different mechanical behaviors of each component. But there is one thing clear. The mechanical properties of these propellants are controlled by the elastomeric matrix. Okay, a motor made of a composite solid propellant has normally long lifetimes of several decades. And during its life, they are going to be subjected to different stages that can be reduced to production, transportation, storage, and operation. And during these stages, the composite solid propellant is going to be subjected to mechanical processes as preparations during transportation and operation, and chemical processes such as the exposure to high temperature or to the atmospheric ambient. And these processes are the causes of aging of the propellant, and aging means the appearance of cracks in the propellant. And these cracks increase the burning area during the combustion process in operation and modify the thrust profile shown in red for the section with cracks. And this can lead to a failure or even to an accident. So when the composite solid propellant is aged, structural integrity issues arise. To perform correct fracture characterization, it is important to choose the adequate fracture mechanics approach. And these materials show a strong viscous effects in their properties. For example, stiffness or relaxation. So the most adequate fracture mechanics approach to use is the viscoelastic fracture mechanics. And this approach depends on two fracture parameters, the pseudo or reference J integral, JR, and the pseudo or reference crack tip opening displacement delta R. As everybody knows, to solve a viscoelastic problem, normally we use the correspondence principle that basically converts the viscoelastic problem into an elastic one. And for the fracture characterization of this material, Shepery in 1984 proposed a particular version of the correspondence principle, making use of a reference elastic body. And this principle states that the stresses, the body forces, and the tractions are the same for the viscoelastic material and the reference elastic body. So if a viscoelastic solid is adjusted to displacement history, for example, rate constant, the load will be nonlinear because of the relaxation of the material, but by the application of the constitutive equations of the viscoelastic material, we can calculate the displacement that must be applied to the reference elastic solid to obtain the very same load evolution as in the original material. This displacement in the reference elastic solid, UR, is obtained through this integral, where U is the actual displacement in the viscoelastic solid, ET is the relaxation function in the viscoelastic solid, and ER is the reference modulus that is constant in the reference elastic solid. Once the equivalence between the viscoelastic solid and the reference elastic solid is established, we can define the fracture parameters in the reference elastic body. So the aim of this work is to study the mechanical response of the fracture behavior of a carboxyl terminated polybutadiene based composite solid propellant with evolution of time and accelerated aging time. The material and the study is a booster propellant shown in gray in this micrograph, and the composition is 54 weight % of ammonium perchlorate, 15 weight % of aluminum, and the matrix is carboxyl terminated polybutadiene rubber. Okay, 3 aging procedures were analyzed. Mechanical agent that consisted in the application of a loading and unloading cycle before the corresponding mechanical test. The level of press strain selected were 15% and 30%. Thermal agent that consists in storing the propellant at a high temperature, a constant temperature of 80 degrees Celsius for 24 and 36 days. That corresponds to approximately 22 years and 33 years of equivalent storage time at room temperature. And ozone aging that consisted in putting the propellant inside an ozone chamber for 14, 21, 32, and 42 days at ozone concentration of 160 ppm. Okay. Regarding the characterization, we measured the cross-linking density using data standard. We performed tensile tests, and we determined the Young's modulus and the wetting stress and the wetting strain that is computed as the transition point from the stress-strain curve. We also carry out uniaxial realization test, and the test consisted in the application of a strain of 30% in around 2 seconds and maintained constant for 30 minutes. And the load was recorded, and from the stress versus time curves, the realization modulus is obtained by fitting the experimental data to the generalized maximum model. Fracture characterization, we use the single edge nose tension specimens. The sharpening of the crack was carried out by razor sliding, and all the tests were recorded because from the surface we measured the crack length station and also the crack tip opening displacement. 2 fracture parameters were obtained: the pseudo J integral JR, that is obtained with a well-known expression where eta is a constraint parameter dependent mainly on the configuration, B the thickness, W the width, A is the crack length, and capital UR is the area under the load versus pseudo displacement curve that are obtained from the actual load displacement curve using the convolution integral. And the second fracture parameter was the pseudo crack tip opening displacement, delta R, that is obtained from the actual crack tip opening displacement that is measured at the surface using the 90 degrees interception methodology, again, using the convolution integral. Okay, let's move to the results quickly. Regarding the cross-linking density, in mechanical age specimens, the cross-linking density is not modified with the level of press strain. In thermally aged specimens, the cross-linking density of the elastomeric rubber is increased with aging time, and the opposite trend is observed in ozone-aged specimens. Okay. Regarding the relaxation response, if we look at instantaneous modulus, in mechanical age specimens, the values are very similar to those of the burst-stream material. In thermally aged specimens, the instantaneous modulus increase in a significant way, and the opposite trend is observed in the ozone-aged specimens. In case of the equilibrium or long-term modulus, the same trend is observed, but I want you to focus on these results, is that the realization occurs at the very first second of the process. Tensile properties, okay. In mechanical age specimens, the weighting stress, and the weighting strain increases with the level of press strain, and the jump modulus is not modified very much. In thermally aged specimens, the weighting stress and the stiffness or the jump modulus increases with aging time, and the opposite trend is observed in ozone aged specimens. Okay, I'm moving quickly to the fracture properties. First of all, the figures on the left refer to the viscoelastic material, the actual material, and the figures on the graphs on the right to the elastic reference material. This slide shows the fracture-resistant curves in terms of the J integral for the mechanical age specimens. First of all, the viscoelastic correction is strong indeed, and once the viscoelastic dissipation is discarded in the reference elastic material, we observe a worse fracture response with the level of press strain, both at propagation and at the values of the energy crack growth initiation. And the reason, okay, mechanical aging produces the bonding of the particles from the matrix. So we have more holes in the material. The very same trend is observed in the resistant curves in terms of the crack tip opening displacement. In thermally aged specimens, again, a strong viscoelastic correction. And once the viscoelastic dissipation is discarded, we observe a better fracture resistance in thermally aged specimens. The reason, the higher cross-linking density, the matrix is stiffer and has a higher load-bearing capacity. In case of the resistant curves in terms of the crack tip opening displacement, so I only want you to focus in the viscoelastic material. The crack tip opening displacement is a measure of the deformations around the crack tip, and in thermally aged specimens, the resistant curves are below those of the pristine material, and the reason is that the matrix is less flexible. In ozone aged specimens, again, a strong viscoelastic correction. We discard the viscoelastic dissipation, and we observe a worse fracture response in ozone-aged specimens. The reason, a decrease of the cross-linking density of the matrix during this aging process. And in case of the resistant curves, in terms of the crack tip opening displacement, the opposite trend is observed because the matrix is more flexible. So I wanted to highlight that we have measured the pseudo J integral and the pseudo crack tip opening displacement independently. But if we plot one against the other, we have linear relationships for all the cases. So this allows us to assume a very simple cohesive model, assuming a constant softening function, and we can define a cohesive stress sigma n as the ratio between the pseudo J integral and the pseudo crack tip opening displacement. And we have even been able to identify, we believe, that this cohesive stress is related to the weighting stress obtained from the tensile test, because we have plotted the ratio between the weighting stress and the cohesive stress, and the values for almost all the cases is close to 1. So the conclusions are mechanical age samples showed lower fracture resistance due to the bonded particles from the matrix caused during mechanical aging. Thermally aged samples exhibited a more stable and demanding crack growth due to the higher number of cross-linked chains in the matrix. Ozone-aged specimen presented a reduction on the fracture performance due to the reduction of cross-link in the matrix. And very important one, the cohesive stress was found as an adequate material parameter and the viscoelastic fracture mechanics approach. So cohesive stress appears to be related to the weighting stress obtained from tensile tests. So thank you very much for your attention.